When I recently interviewed candidates for a senior JavaScript engineer role, I was surprised to see how many people didn't understand the difference between primitive and reference values, or variables. Some knew the distinction, but almost nobody could describe how variables interact with computer memory, which I think is quite a useful way to think about it. What I want to do in this video and the next one as well is cover this topic but in a more generic way so that you guys can apply this knowledge to almost any programming language out there. In the first part, which is this video, we're gonna remind ourselves what variables are. In this part, I'll also mention one important thing that's often not talked about when it comes to variables. Then we're gonna look at something that I call data variables. These are variables that point to memory cells where actual data is stored. You'll see how with these we can even store complex data like strings, objects, and arrays. But doing so has some limitations, as we'll discuss in this video in detail. And because of these limitations, it's not very commonly done. And in the next video, in part 2, we're gonna see how reference variables are a solution to these limitations. I'll explain to you in great detail what they are, and I'll show you a few cool analogies. And finally, we look at the caveats with reference variables. Okay, let's jump into the first section. A variable is a name that references a memory cell. Here on the left, I've defined a few variables, and as you can see, each of them is a name that is associated with some memory cell where its data is stored. For example, age is associated with location number 1 and the value 55 is stored there. Height is associated with location number 2 and the value 1.93 is stored there, and so on. When I think of variables, I usually think about two operations that we can perform with them. I call one of them write, as you can see here. We put something in the memory cell associated with the variable. And the second one, as you can see down here, is called read, where we retrieve the values stored in the associated memory cells. We can think about variables as a tool for us programmers to communicate with computer memory. Throughout this video and the next one as well, you'll see these labels next to our variables. I put them here so that you can clearly see which memory cell a variable is bound to. For example, here you can see that the variable age is bound to location 1. The important point that I mentioned earlier in the video about variables that's often not talked about is once a variable is defined, the variable will only point to one address directly. It will only be bound to one address directly. For example, whether we have 1,000 lines of code here or just 4 lines of code, the variable age will always be bound to the memory address 1. I need to quickly mention a few words about our memory here on the right, as some of you may have some questions. As you can see here, our memory address is a decimal number, and our memory values are also human-readable values, but this is not the case in real programs. As you know, data is represented in binary in computers, so the value 55 would be in binary, and the memory address would also be in binary. Also, throughout the slides, we'll only have up to 999 memory cells, but real computers can have billions, if not trillions, of memory cells. Now that we've reviewed variables, let's talk about what I call data variables. As I said before, a data variable is a variable whose cell contains actual data. In the next few slides, I'm going to show you how we can store different types of data, including more complex stuff like objects, lists, and strings. On this one, we see how primitive values like 55, 193, true can be stored directly in the memory cells where the variables point. Please note that in reality, the number of memory cells per value may differ. In case you guys are still struggling to understand it, let me show you an analogy. Here we have a guy in pants, and the guy has a pocket right here. You can think of the pocket as the memory cell of our variable. Inside of his pocket he has the actual value Snickers. He doesn't have a key to any other place that stores Snickers. He doesn't have money to buy Snickers. He has Snickers directly in his pocket. Now let's see how we can store more complex stuff directly in memory. Okay, here we have strings, which is quite interesting now, right? Here on the left, we have the variable called hair color, and it has a value black. As you can see, hair color points to the location number 1. But since black is a sequence of characters, there is not enough space to store it in one location. Because of that, each character is stored individually, as you can see on the right. B is stored in location 1, L in location 2, A in location 3, and so on. This character at the end is something that C and C++ and maybe some other languages as well do in order to indicate the end of the string. Now you might be asking, how would this value be read if hair color points to location 1? So when the value is retrieved, subsequent cells will be read as well until this character is encountered. Additionally, if you want to access individual characters of the string, as you can see here with this bracket notation, it can be done by using the so-called offset like here. So in the first example, the calculated address will be 1, the address of the variable, plus 0, which results into this. In the second example, the address will be 1 plus 4, which is 5, which is this location right here. But the last example is bad access because it goes beyond the memory space of the string. I hope this makes sense to you. Let's now go to the next one. Our next one is lists. Here we have a list called favorite numbers. It points to location number 1, and it has values 2, 4, and 6. Similarly with strings, each value of the list is stored in an individual cell, as you can see on the right. And in order to access elements of the array, we can also use offset notation like with strings. So here, the address that we'd go to is 1. In this case, it is address 3 because 1 plus 2 over here is 3 and we'd get 6. But here on the last one, we may go beyond the allocated space for the array. So this operation is unsafe. Lastly, let's see how we can store objects. Here on the left, we have a variable called person. It points to location number 1 right here. And this variable holds a complex value with 2 fields or 2 properties, age and height. The way it could be stored is similar with lists, where a field could be associated with an offset value, like here, 1 plus 0 for age and 1 plus 1 for height. So if we want to access age, this field of the object, then the resulting address will be 1 plus 0, which is 1. We'd retrieve the value 30. And if we wanted to read height, the resulting address would be 1 plus 1, which is 2, and we'd retrieve the value 175 from here. We've looked at all of the values that I wanted to show you. Now I want to talk about why it's a bit problematic to do so for complex values like objects, strings, and lists. Although it's not impossible because some languages do it, like C and C++, and I'm sure that some others, there are certain circumstances where direct storage makes sense. I'm going to talk about the 3 main reasons why it's problematic next. Problem number 1 related to direct storage is static size. We have a variable called hair color with the value black. The variable points to location 1 and its value is stored in this memory segment. Next, we define the variable age and assign the value 55 to it. Notice how age points to location 7. And also notice how 7 goes right immediately after the string memory space. What we attempt to do next is assign a different value to our variable hair color. But the value we're trying to assign is longer than the previous value. It has 6 characters instead of 5 characters that we had space allocated for. So there is no way for us to expand beyond cell number 6. You might be asking, could we store the characters elsewhere and then somehow access them? And the answer is yes, but not with direct storage. Remember what I said to you at the beginning, is that once a variable is declared, it is bound to a certain location. So hair color will point to location 1 here on this line and location 1 on this line as well. We would want a different way to point to the new data, but keep using the same variable. Let me show you an example with arrays now. We have a very similar situation here. Please have a look and pause if you want to look at the details. Let's now go to the next problem. Problem number 2 is memory footprints or memory consumption. On the left, we have the same variable hair color with the same value black as we had previously, and then we declare another variable called hair color copy, and we assign the value of hair color to hair color copy. As hair color copy is a different variable, it'll point to a different location. In this case, it points to location number 9 of our memory. Note how the entire value of black was copied over to the memory space of the variable hair color copy. Now imagine if the size of the string was not 5 characters but maybe 5,000. The impact would be much more significant, right? So it would be 10,000 cells plus 2. But to add even more to that, in real programs we pass data around all the time. And we can end up in a situation where the value black can be copied hundreds of times. Let me show you an example with arrays. Here we have a favorite numbers which points to location number 1. And then what we do below is we pass favorite numbers to this function or procedure called print numbers. Now, in some languages, this can result in copying the entire value of favorite numbers onto the local variable called numbers. If you're not familiar with functions yet, please don't worry. I just want to illustrate how memory footprint is a problem with direct storage. Now let's go to our final problem with direct storage. Our last problem is expressing relationships. On the left, we have this graph that shows different people and their relationships with each other. For example, John and Stephen are friends. Stephen and Jessica are friends as well, and Jessica and Sophie are friends. But notice that Sophie and Stephen are not friends, and Sophie and John are not friends either. Also notice that Stephen and Jessica have 2 friends. With direct storage, it would be really problematic to express these relationships of friendship. Let's take John, for example. John's data could be stored here, but where would we store data for Stephen? We could incorporate the data for Stephen directly here in John's data, but then it would be problematic. The reason for that is that we would need to copy it for Jessica as well, because Jessica is also Stephen's friend. But then imagine if you wanted to modify data for Stephen. It would be quite problematic. We'd have to modify it both in John and Jessica. So there needs to be another way where both John's data and Jessica's data point to where Steve's data is stored. Without having references or links, it would be close to impossible to express certain structures in computer memory. Okay, that's it for part number 1. In the next video, you'll see how reference variables are a solution to the problems that we looked at today. I'll also explain to you what they are, I'll give you some analogies, and so on. I'll see you then. Bye-bye.